Hello, this is Graham Neubig and welcome to CS 11747. This time I'll be talking about advanced sequence models and in particular sequence pre-training methods that can be used to improve our effectiveness on sequence models. I'd like to thank Pengfei Liu for making most of the slides here. Okay, so if we remember, we have previously talked about pre-training methods for masked language models like BART or Roberta. And basically the way these models work is by taking in a sentence that has some of its words masked out, running it through a transformer model, which considers both left and right context, and predicting the masked out word. So this is a very powerful tool, obviously, and widely used in NLP, but in general, only the encoder is pre-trained through these methods, and it's not suitable for conditional generation, for example, which is also a very broadly used class of NLP methods. So one question becomes is how can we design a pre-trained model or model pre-training method that can adapt to conditional generation? So there are actually quite a few different methods that do this. And here on the left, we have the traditional masked language model. And one way that we can train models is using encoder-decoders. And encoder-decoders, as we've talked about before, basically we have an encoder that encodes things kind of bidirectionally using, for example, a bidirectional LSTM or a unmasked transformer. And then we have a decoder which encodes things unidirectionally by basically taking in the encoder states and then on the decoder side, only considering the previous context. So the encoder is bidirectional, the decoder is left to right. Also notably, the parameters of the encoder and decoder are not shared. We use separate parameters most of the time anyway. So these models can be used for pre-training, and there are methods like MAS or T5 or BART, which we're going to be talking about shortly. And then on the other hand, there's another variety of kind of sequence or conditional generation models that essentially treat all of this as a single language modeling problem. But instead of having an entirely left to right language model, on the input side, we have bidirectional attention that encodes all of the prefix appropriately. And then on the decoder side, where we actually generate the inputs that we would like to generate, we have a left to right decoder. And notably here, the parameters are shared. You'll see all of these boxes are blue. So just to summarize, encoder-decoder model, we have a bidirectional encoder, unidirectional decoder, and the parameters are not shared. And in the prefix LM, we have a bidirectional encoder of the input, unidirectional decoder for the output, and the parameters are shared between them. So there's a bunch of pre-training methods, and the first pre-training method that I'm aware of that was used for seek-to-seek tasks was a paper by Ramachandran et al. And basically the model, what it does is it trains an RNN-based encoder-decoder model, and the objective is just a left-to-right language modeling objective. So the encoder and decoder are pre-trained using two left-to-right language models using standard objectives. The data that was used here was task-specific, so they used different data depending on the output that they wanted to apply to. So that paper was from 2017, I believe, and then recently there's been, in 2020 or so, there's been a big proliferation of all of these different pre-training methods. One of them is mass, and a lot of these are pretty similar. Basically, they consist of masking out certain spans in the input and predicting them in the output. And the way all of them use transformer-based encoder-decoders because it's kind of the default way of doing things right now. And so the way mass works is it basically masks out some subset of the tokens on the input, and then it predicts the masked spans. So it doesn't bother predicting the spans that were left unmasked, and it was trained on some web text data. There's also the BART model, and the way the BART model works essentially is it is a transformer-based encoder-decoder model again, and the way it works is by reconstructing the original sentences in the decoder from corrupted sentences in the input. And there are lots of different methods that are used for this corruption, such as deleting tokens, masking out tokens, permuting the order, rotating documents, and trying text and filling tasks, basically. So they try all these different types of corruption, all with the goal of replacing kind of new or recovering the previous output. And it was trained on lots and lots of different data, the books corpus, CC News, web text, and stories. This variety of method has also been applied to multilingual learning. And the way it works basically is just you take data from a lot of different sentences and feed it into a BART style model along with a language tag, which the language tag is basically used to indicate which language you're handling. And so they have a transformer-based model that uses multilingual denoising autoencoding, where the goal is to reconstruct original sentences from the corrupted output. And they use a common crawl 25 corpus over 25 languages, which just contains lots of text from the web. And if we compare regular seek-to-seek models with regular masked language models with respect to performance on sequence style tasks, such as summarization, we can see that a model that was trained using BERT, or that uses BERT as its encoder, just is quite a bit different with respect to the final score that you achieve than the BART model. So if we compare BERT and BART, there's about a 2 rouge point difference, and this is quite large in summarization tasks, which kind of demonstrates the importance of doing this decoding, this sequence pre-training. In addition, for non-generation tasks, interestingly, the seek-to-seek model can achieve comparable or even better performance than masked language models. And we can see that for different varieties of tasks, the values are comparable or even, a little bit better, a little bit worse. So the specific way that you can use BART for tasks like this, or sequence pre-training methods for tasks like this, is basically by taking in the hidden states of the BART model run over the sequence and using these in place of the hidden states from Roberta, for example. So now moving on to prefixed language models. Prefixed language models, we have the encoder and decoder input into the same model by basically using fully connected self-attention for the input, which is on the black on the left side here, and then left to right self-attention, which is in the green on the right side here for the outputs. One example of this is UniLM, and basically the way this works is if we have different segments, we might have sometimes the segment processed with the left side and the right side with kind of fully connected self-attention and left to right self-attention. We might also process just left to right, and we might also process fully connected for both segments. So basically this gives you, in a way, the best of all worlds, in that this over here is a little bit like, BART or Roberta. This over here is a little bit like the seek-to-seek models that we talked about before, and this over here is a little bit like, a traditional left-to-right LM, like GPT-2 or something like that. This was trained on English Wikipedia and the book's corpus. So T5 is it's a model, I guess you could say. It's a single pre-trained model, but they also, in this paper, do a pretty extensive exploration of different design decisions that go into the pre-trained model. And so I can definitely recommend taking a look at this paper from that respect. So they try a left to right LM, prefixed LM, and encoder decoder with several different objectives. And they also train it on a very large corpus of kind of web scraped text, Wikipedia, news, and other web text. So, for example, they try prefix language modeling, where they have the inputs and then they have the targets. They try a BART style approach where you try to generate the original text. They deshuffle, they do a mass style approach, and they replace spans, they drop tokens, pick random spans, and many other different things. So there's a pretty extensive exploration here. So as I mentioned before, there's some differences between these two. Seek-to-seek has different parameters for the encoder-decoder, and the prefixed LM has the same parameters for the prefix and the continuation. And also, the way the encoder state is passed on to the decoder state in seek-to-seek models is usually that the encoder state, the last encoder state, is used as opposed to passing it through each layer. So that's another difference as well. The loss function, seek-to-seek calculates the loss only on the output, whereas the prefix LM can calculate the loss on both the prefix and the continuation. So, these are also, these are two kind of similar methods that both attempt to take in an input and calculate an output. However, another thing to note is that it is also possible to do pre-training with, for example, a left-to-right language model, and then just use it in a way such that the input is the prefix that you feed into left-to-right LM that then processes the suffix. And this is the approach taken, for example, by GPT-2 and GPT-3. So GPT-3, I'm sure a lot of people in the class have heard about it at the moment. So basically, the model is similar to GPT-2, which we've already talked about in a previous class. It's just a left-to-right language model using transformers. trained on a lot of data from Common Crawl, web text, a books corpus, and Wikipedia. So the interesting thing about GPT-3 is the experimental results that they demonstrate in the paper basically suggest that a left-to-right language model, I wouldn't necessarily say it is all you need, but it's surprisingly powerful at doing different tasks. And maybe the more interesting thing is that they demonstrate that you don't actually need to fine-tune the parameters of the model downstream. So like in all of the previous methods that we talked about before, you essentially take the model and then you fine-tune it to do a task. But what they demonstrate in this paper is that with the help of a prompt, many NLP tasks could be formulated as a language modeling problem. So as an example, if you want to translate a French sentence into English, you would take the French sentence and then say comma, translate it into English with a prompt, and it would actually output this. And this could be done with any language model. It's mostly that GPT-3 is a particularly large language model trained on lots of different data, so it demonstrates, it achieves better performance at these kind of few-shot tasks than some other models. Another example from this website, buildgpt3.com, is generating a Python function. So you take the input and you say def is palindrome, and you give a docstring, check whether the string is a palindrome, and it actually outputs something like this. And this is most likely because it was trained on lots of Python code as well, and there are is palindrome functions in the Python code that it was trained on, so it's able to effectively reproduce this. And it can even move beyond just memorizing and generalize to some extent. Some other examples are if you could give multiple prompts, then it can answer, like it can learn patterns. So you start out with Q and ask a question and then give A, which gives the answer to the question, and you do this 5 times, and then 5 is an arbitrary number. It could be one time, it could be 5 times, it could be 20 times. And then you follow with another question where you don't know the answer to it, and it can output answers, basically. So I think it's worth talking about why this is even possible in the first place. And the answer to this is language modeling itself is a very versatile task, essentially. So we have lots of different, just to model the likelihood of the data, if we have lots of different types of data that we are modeling, then it makes it quite, plausible that we would have data with similar patterns somewhere in the internet to something like this. So for example, you might have a magazine that interviewed a singer or a famous other variety of celebrity, which has Q, and then it has A, and then you're having a conversation like this. So in order to model that conversation in your training data, you would also have to essentially learn these patterns. So if we think about pre-trained models of various varieties that we talked about before, we talked about masked LMs, encoder-decoders, prefix LMs, left-to-right LMs. And we can essentially create a table like this where we have X and we have Y. And we can look at the attention mask, the variety of corruption we apply to the data, and the prediction objective for both the inputs and the outputs. And if we're talking about a masked LM, we really only have an input, and we have a fully connected attention mask. We mask tokens or spans, or maybe replace them, and we predict the masked words. In left to right LM, both in the prefix and the suffix, we have an autoregressive language model with no corruption, and we predict over all words. So basically, we're just predicting left to right throughout the entire sequence. For the prefix LM, we replace the masked LM. We replace the input with the masked LM, but then we have a autoregressive LM on the Y side. So you can see it's a very nice combination of the first one and the second one here. And then for the encoder-decoder, it's very similar, except we are trying to basically drop or replace words, and then on the output side, we're trying to recover the original value. So I think this is also interesting to view things this way, because it also shows that there's a huge design space that isn't yet covered by these models. So you can think about what it would mean to change some of these design decisions in interesting ways. Okay, so some practical tricks if you actually want to use them in your work. So you want to choose the appropriate one. For example, you'll want the data and the loss of the pretrained models to match the domain or the characteristics of your tasks. So empirically, usually larger versions do better. For example, Roberta is better than BERT on many NLP tasks, but when designing a metric, such as BERT score, BERT does better. And, there are many different nuances that go into training these models, including the data, the objective function, how long it's trained. And when you consider all of these, a lot of the final results that people get do make quite a bit of sense. Also, for example, BART is, or other seek-to-seek training methods do a lot better than having a BERT-based encoder on text generation tasks, mostly because an encoder-decoder model is trained to do text generation tasks. Models like GPT-2 are good for unconditional text generation tasks, trained language models. GPT-2 can also be used for few-shot or zero-shot learning. And I actually encourage you to do this if you have access to, or if you're able to, download or use an online demo of GPT-2. It's actually kind of fun to play around with it. But GPT-3 or other larger language models in GPT-2 are likely to do better because they're trained on more data and they have more parameters, so they can memorize the data they have seen better. Also, economy, there's different versions, like the base version, the large version, the huge version. When you're experimenting, you don't need to jump to the huge version right away. You can use the lighter version first. And also, if the pre-trained model is too large to store for GPUs, there's a lot of work on knowledge distillation. And you can use data or model parallelism to help you out as well. And also, you need to be careful when you're using them. You need to think about what are the data preprocessing methods, so make sure you get that right. Do you want to fine-tune or freeze the parameters? And if fine-tuning, what types of fine-tuning methods do you want to adopt? And we're not going to go into these with lots of detail here, but we gave some references for you to take a look at. Another thing is, if you have a pre-trained model that you're interested in, for example, BART, has it already been tuned by another relevant task? So like, let's say we have the BART training objective. there are versions of BART that have already been fine-tuned on a summarization task, and if so, you might be able to use the model directly or further fine-tune from that model to improve your performance. So there's lots of open questions in these models as well. So for example, the data that they're trained on, if it's just scraped from the web, there's a number of problems that could happen. So for example, if you have a data set that you're testing on that has also been created from the web, it's quite possible that the model has already kind of memorized the training samples that the test samples that you're trying to evaluate on. So in which case you get unfairly high performance. Another issue is data privacy. So the pre-training data can actually be recovered to some extent from the model itself. So essentially, if you query the model in particular ways, this allows you to recover the model, which has serious privacy concerns. And downstream task-specific pre-training. So if you think of it from a data perspective, pre-training on in-domain unlabeled data can improve performance on downstream tasks. You can also think of it from a loss function perspective. So like summarization specific pre-training models or co-reference specific pre-training models. And how do we use it? Should we be fine-tuning all of our models, or with sufficiently large and powerful models, do we not need fine-tuning, like what was suggested by GPT-3? And also, is it true that a large pre-trained model is all we need? So there are arguments that essentially, if you're just training on text, you're never going to learn about, for example, the world. You're never going to learn about the association with images and other things like this. And this is an area of very interesting and active research. So that's all I have for today, and I'm looking forward to discussing more about this very timely